This is the second video regarding the missed class on May 2nd, 2018. We just finished talking about Q and found that in the previous problem that we had done, that Q, the reaction quotient, determined by inserting the given concentrations into the equilibrium expression. We determined the reaction quotient in this case was bigger than the equilibrium constant, so the reaction was not at equilibrium, because if they were at equilibrium, they would have equaled each other. So since Q was too big, we needed less product and more reactant to get this ratio down, to make it smaller. Since we need less product, we need less of these guys and more of this guy, so the reaction will proceed to the left. So the answer to the how much reacts question is it goes, we don't know, but we know it goes down on this side and it goes up on that side. Conversely, if Q had been less than the equilibrium constant, then we would have had the opposite happening. And we would have needed more of the numerator and less of the denominator, so we would need more products and less reactants, and so the reaction would proceed to the right. And that would apply if Q is smaller than Kc. So now looking at the next question, you would need to take these moles and divide by the number of liters to get molarities. Set up the expression of the concentration of SO2 multiplied by the concentration of chlorine divided by the concentration of the SO2Cl2. Put the concentrations into that equilibrium expression. If the system is equal, when you divide the concentrations by each other, you'll end up with 0.011. And if you don't get 0.011, the system is not at equilibrium. And there's your first answer, if it's not at equilibrium. So if it's not at equilibrium, which way will it move? Well, then it goes back to the value of Q compared to the equilibrium constant. All right, down here, same kind of problem. This one, part A, is pretty simple because there is no product, so you know it has to go right. Now we're down to another concept that I wanted to introduce today called leChatelier's principle. So I'm going to rewrite this equation over here so I've got a little room to play with it. It's the N2O3 equation, yield, in equilibrium with NO and NO2. On this side, you put heat. How do we know that heat goes over here, or you could say energy here? How do we know? Because this is positive, and what's a positive change on delta H mean? Endothermic or exothermic? It means endothermic. All right, so leChatelier's principle. A system at equilibrium will stay at equilibrium unless subjected to a stress. So it'll stay at equilibrium forever until some kind of stress goes on it. If you think about if you have a bottle of water with a lid on it and it's condensing on the sides, the condensing doesn't stop when the water's on the side of the bottle. It continues to condense, but there reaches a point where evaporation occurs at the same rate, and so that's called equilibrium. And it'll keep doing that forever unless the temperature changes. Now if you raise the temperature, you get more water in the vapor phase. So you've shifted the equilibrium. The same thing happens in chemical reactions. So this system will go back and forth forever until I put a stress on the system by changing a concentration of something or changing heat or by changing a container size. So let's first of all look at what would happen if I were adding more NO2. So if that was my initial stress and I increase that, wouldn't there be more contact here with the NO? And if there was more contact, there'd be more reaction. You'd make more of this, wouldn't you? So we would say that when you increase the NO2, the equilibrium system will shift in this direction, creating more of that. So that's going to go up. Now, of course, if that goes up, this has to go down. Remember that when you divide the products of these two things by that you always get the same number. As long as temperature doesn't change, that ratio stays the same. So if I raise this, these guys have to adjust to keep the ratio constant. All right, so if my initial stress was to raise that, it would go that way. All right, if I were to pull this stuff out as my initial stress, I take that away, there has to be some of this reaction with this to make that. So if I take this out, then part of this will decompose to replace what I took out. So the equilibrium would shift in this direction because that's decomposing to make more of this that you took away, and consequently it's also going to make more of that. So this is going to go up on that side. And over here things would go down. So this is a pretty brief treatment, but you can see that equilibrium shifts away from an increase and toward a decrease. So if I increase this, equilibrium shifts in this direction. If I decrease this, equilibrium shifts in that direction. So it shifts toward the decrease, toward a decrease. If I increase this, it shifts that way to make more of this. So we'd say that's away from an increase. Okay, if I was to raise the temperature, what would happen? Well, same rule applies. It'll shift away from the increase, so the equilibrium would shift this direction if I raise the temperature. So that just leaves one other thing to consider, and that's pressure. We know from previous experience that when pressure goes up, what happens to volume? It goes down. So if I was to, let's just look at letter A here, if I decrease the container size at constant temperature, so that's decreasing the container. That means that the volume is going to decrease, the pressure will go up, but and normally, sometimes these questions say you change the pressure. Like right here, the pressure on the system is reduced. So if you change the pressure, the volume will react accordingly. In this case, I have a mole here and a mole here. So I got 1 mole and 1 mole of gas on the right side of the arrow. On this side, I've got 1 mole of gas on the left side of the arrow. But on this side, how many total moles are there? There's 2. So if I increase the pressure on the system, decrease the volume, it's going to favor the side or shift toward the side with less moles. So if I increase pressure, it's going to go this way because there's less moles over here. If I decrease the pressure, like pressure down, volume would go up. So that would favor the side with more moles of gas. So if I was to lower the pressure on this reaction system, then these two guys would go up and this would go down, as equilibrium would shift toward the more space. Okay, this pressure volume stuff only applies to gases. So if you increase the pressure or decrease the volume, then the side that has less moles would be favored. So in this case, 2 moles here, 1 mole here. It says decrease the container size, so you're making less room, so it's going to shift the equilibrium to the side that would take up less volume. Because 1 mole of a gas, if it was just all on this side, would be what, 22.4 liters? But on this side, 2 moles of gas, if everything was on that side, would be 44.8 liters. So which is bigger? This one. Which is smaller? This one. So if you increase the pressure or decrease the volume, you're going to favor the side that's smaller. And if you increase the volume, you favor the side that's larger. So based on this, you need to give a shot to all these questions that we have. The remaining questions are primarily either non-mathematical or minimal math. The beginning questions were harder mathematically because they often had a quadratic in them or square rooting and such. Be sure that you can do all of these problems by Friday. And don't forget that you have the thermodynamics quiz that's supposed to be turned in. So that's the end of my makeup class for today.